Section 3.9, Rational Functions. The objectives of this section are to evaluate limits involving infinity and interpret the results in the context of asymptotes, and also apply curve sketching techniques to graphing rational functions. And let's begin with asymptotes and limits involving infinity. First off, we have the definition of a vertical asymptote, and it's the following. If f of x approaches infinity or negative infinity as x approaches some constant called c, either from the left or the right, then we say that x equal to c is a vertical asymptote of the graph of f. So simply stated, if the function goes up or down forever near a number called x equal to c, then we say that x equal to c is a vertical asymptote. We can see that in the graphs that we have over here in the middle of the page. X equal to c is some random number. In this case, both values are negative on the negative side of the x-axis. And we can see that as x approaches c from the left side on the first graph, the function goes down forever. And when x approaches c from the left on the other second graph, the function goes up forever. And similarly, when x is approaching c from the right on both graphs, we can see that the graph either goes up forever or down forever. Regardless, this is all saying that the limit of f of x as x approaches c from the left or right is either plus or minus infinity, meaning the limit does not exist. The function just goes out of bound. So that makes x equal to c into a vertical asymptote for the function f. Now, to find vertical asymptotes, usually it involves looking at the denominator and seeing the values that make it equal to 0, then deciding whether those values represent a vertical asymptote or a hole. A hole is just basically simply a gap in the graph of the function. So the function does not blow up towards infinity or negative infinity. It just stays relatively the same level. It just has a little hole in the graph. Now, to find out whether you're dealing with a vertical asymptote or a hole, there's usually some procedure that we can follow. You can either find the limit as x approaches to c, and c in this case is going to be the number that makes the denominator equal to 0. Or if you want a little shortcut, you could just plug the number that you think is a vertical asymptote into the numerator. And if you see that the numerator of the function is not equal to 0, then you have in fact found a vertical asymptote. But if the number that you're testing makes the numerator equal to 0, then the number you're dealing with is not a vertical asymptote, but instead it is a hole. So to verify and to look at an example, let's take a look at example number 1, where f of x is equal to x squared plus 3x plus 2 divided by x squared minus 4. It's asking us to determine any vertical asymptote for this function, f of x. So as we said, the first thing you want to do is grab the denominator, in this case x squared minus 4, and figure out what makes it equal to 0. Now, I can factor this x squared minus 4. It looks like a difference of squares. I can write it as x minus 2 multiplied by x plus 2 to quickly find the numbers that make the denominator equal to 0. And because this is a product, I can either set the first parentheses to be 0 or the second one to be 0 according to the zero product property, which means that either x is equal to 2 or x is equal to negative 2. So those two values are the numbers that make the denominator equal to 0, and they may or may not be holes or vertical asymptotes. So how do we check? I could either look for the limit as x approaches 2 from the left or the right and see that it's plus or minus infinity, do the same thing again with negative 2. Or, if I want a quick shortcut, I just grab the 2 or the negative 2 and I plug it into the numerator of the function f of x. So let's try it out. Let's see what happens if I plug in 2 into the numerator of the function. So obviously, when I plug 2 into the function, I'm going to get 4 plus 3 times 2, which is 6, plus 2 divided by 0, because 2 minus 2 multiplied with 2 plus 2 will be 0. And this will be basically 12 divided by 0. So it has the form of a constant that is not equal to 0 divided by 0. So that means that I'm dealing with the form c over 0, which means that in fact x equal to 2 has a vertical asymptote. So instead of writing the full word, I'm just going to write VA for vertical asymptote. Now let's do the same thing with negative 2. So I'm going to plug negative 2 into the function and see what ends up happening. So on the denominator, I know it's going to be 0 because negative 2 minus 2 multiplied with negative 2 plus 2 will be 0. But on the numerator, I'm going to end up with 4 minus 6 plus 2, which is basically 0 over 0. So the form now is 0 over 0, which means what I'm dealing with here is just simply a hole in the graph, not a vertical asymptote. Now, obviously, we can also try to find the limit as x approaches 2 from the left or the right and see that it's either plus or minus infinity. That would confirm that x equal to 2 is a VA. We could do the same thing with the limit as x approaches negative 2 from the left or the right, and we will find out that it's not equal to infinity or negative infinity, which means, in fact, that we're dealing with a hole at x equal to negative 2, but I'm going to skip the limits for this problem. Next, let's discuss horizontal asymptotes. And as the name implies, this is a horizontal line. We usually say that it's y equal to L, capital L. And we say that it's a horizontal asymptote for the function f of x if the limit as x approaches infinity for the function f is equal to L, or if the limit as x approaches negative infinity on this function f of x is equal to L. So basically, the difference between this particular limit and the previous limit on the previous page is that now we're letting x go to infinity or negative infinity, and we're trying to find out if the function f of x becomes sort of constant, sort of stable at the end of time. And we can see that this is what it looks like on the graph. You have a horizontal line, and the function tends to get close to it as x goes to infinity or negative infinity. Now, since we're going to be dealing with rational expressions in this section, it's usually helpful to know these two rules, and they involve what to do when you have a constant divided by x to a power and vice versa. So if I have a constant divided by x to some power and x is going to infinity, then the limit is equal to 0, and vice versa. If the x is on the numerator and it's raised to some power, and there's a constant on the denominator, then the limit as x goes to infinity will be infinity. So let's take a look at example number 2, where we have a bunch of limits that we have to evaluate, and this is going to help us talk about what's called the end behavior of the function. So for the first limit, we're told to find each limit, and the limit here has x going to infinity with x cubed plus 4x minus 1. So here's the thing. Since x is going to infinity, and I'm dealing with x cubed plus 4x minus 1, it's a polynomial. The polynomial is going to behave just like the x with the highest power. This only happens when we're approaching infinity or negative infinity. So in other terms, I can ignore the 4x minus 1. I can pretend that they were never there and just look for the limit as x goes to infinity of just simply x cubed. This is what we call the end behavior of the function. So the polynomial x cubed plus 4x minus 1, if you graph them together on the same graph, you'll notice that they both behave the same way as x becomes larger and larger. This is why I'm kind of ignoring the 4x minus 1 because my x is approaching infinity or negative infinity. Remember, I can only do that if x is approaching infinity or negative infinity. And in this case, I'm going to end up basically with infinity to the power of 3, and a big number multiplied by a big number multiplied by a second big number is going to be a really, really big number. This is not a constant. In other terms, the limit does not exist. So unfortunately, this function, x cubed plus 4x minus 1, does not have a horizontal asymptote. So I'm going to write no HA for no horizontal asymptote. Similarly, if I'm taking the limit as x goes to negative infinity of x cubed plus 4x minus 1, again, since the limit has x approaching negative infinity, I'm going to ignore everything except the leading term. So I'm going to ignore the 4x and the negative 1, and I'm just going to take a look at what happens to the limit as x goes to negative infinity of x cubed. And in this case, it's a negative raised to the power of 3, so it's a negative infinity solution. And again, that implies that the function that we're working with, x cubed plus 4x minus 1, has no horizontal asymptote, unfortunately. So in deciding the end behavior of the function, you always want to take the highest exponent with the x. So in both of these cases, it was x cubed. For the next one, we have the limit as x approaches infinity with the negative 2x cubed plus 4x minus 1. And again, because I am approaching an infinity or a negative infinity, I'm going to look at the end behavior of the function. So that means I'm going to ignore the 4x minus 1, and I'm just going to look at the highest x with the highest power and whatever constant is got next to it. In this case, is negative 2. And so the limit in this problem will basically be equal to the limit as x goes to infinity with negative 2x cubed. And in this case, I'm going to plug in the infinity into the x. And so what am I dealing with? I'm dealing with the negative 2 multiplied by infinity to the power of 3. Infinity to the power of 3 is going to be infinity multiplied by negative 2. The whole thing is going to be negative infinity eventually. And again, that means the function that I'm working with does not have a horizontal asymptote. Okay, moving on to the next one. The limit as x goes to negative infinity with negative 2x cubed plus 4x minus 1. Again, the limit has x approaching negative infinity, so that means I'm going to ignore the 4x and the negative 1 and just only pay attention to the leading term, which is negative 2x cubed. So it's the limit as x approaches negative infinity with negative 2x cubed. And so I'm going to have negative 2 multiplied by negative infinity to the power of 3. Negative infinity to the power of 3 is going to be negative infinity. Multiplied by negative 2 is going to make it positive infinity. So again, no horizontal asymptote for this function. Okay, the next one we have the limit as x going to infinity. And we have a numerator and a denominator. So this is going to be much more interesting. So we have the numerator 2x squared plus 3x minus 4, all divided by 6x minus 3x squared. So according to the rules that we've mentioned, we are going to ignore everything except the leading term. So on the numerator, I get to ignore the 3x and the negative 4 because the leading term is just simply 2x squared, and I can do that because the limit has x approaching infinity. On the denominator, what I'm going to ignore is the 6x because technically the negative 3x squared has a higher exponent. So this turns into a limit with x approaching infinity, and the numerator will be 2x squared, and the denominator will be negative 3x squared. And so if I reduce the fraction to lowest terms, I can divide the x squareds, and I'm going to end up with the limit as x approaches infinity with 2 divided by negative 3. There are no more x's left over because everything got canceled out. And the limit of this is just negative 2/3. And as you can see, the answer did not turn out to be infinity or negative infinity. So what does this mean? This means that the function 2x squared plus 3x minus 4 divided by 6x minus 3x squared has a horizontal asymptote. So we're going to write y equals to negative 2/3 is a horizontal asymptote. So I'm just going to write is HA for shortcut. So as you can see, when the function is a rational expression with a fraction, things are a little bit more interesting. So here we go again. We have a limit as x goes to infinity with 5x plus 7 on the numerator, all divided by x squared minus 2x plus 1. And again, since x is going to infinity, I'm going to consider the end behavior. So I'm going to ignore the 7 from the numerator because 5x is the leading term there. And on the denominator, the leading term is x squared. So I'm going to ignore the negative 2x and the plus 1. So my limit turns into something slightly easier. The limit as x goes to infinity with 5x on the numerator and just simply x squared on the denominator. And before I go ahead and plug in infinities everywhere, let's reduce the fraction to lowest terms. This makes it even easier. So we can divide one of the x's on the numerator and one of them on the denominator. So we'll be left with the limit as x goes to infinity and just simply 5 divided by x. And so this is basically 5 over infinity And this is what we mentioned earlier in the theorem. When you have 5 divided by infinity, when you have a small number divided by a really, really large number, the answer is going to be equal to 0. And as you can see, it's not infinity. The result is 0 in this case. So what do we say at the end? We say that y equal to 0 is a horizontal asymptote of the function 5x plus 7 divided by x squared minus 2x plus 1. So hopefully this is making sense. So try the next one on your own before I reveal the answer. So take a minute to pause the video and see what you get for this limit. Okay, hopefully you had some chance to pause and solve the problem on your own first. But let's take a look at it together now. So my x is approaching infinity again. So I'm going to grab the leading term from the numerator, which is x cubed, and the leading term from the denominator, which is x. I get to ignore the 7x plus 5, and I get to ignore the negative 4, because my x is going towards infinity or negative infinity. And so my problem is now reduced to the limit as x goes to infinity with x cubed on the numerator divided by x on the denominator. And obviously we can reduce this to lowest terms. When you divide x cubed by x, you just get simply x squared. And so this is going to be infinity squared, which is infinity. So in other terms, the limit does not exist. So the function does not have a horizontal asymptote. Just like the first few that we did where we had polynomials, all of those have no HAs. So this one has no HA, this one has no HA, no horizontal asymptote for those functions. And similarly, this one again has no horizontal asymptote. So the function x cubed plus 7x plus 5 divided by x minus 4 does not have a horizontal asymptote. Now, finally, the last problem is slightly different because it's not a rational expression. It's a constant added to a rational expression. So how do we deal with these types of scenarios? Well, it's straightforward. We just plug in the infinity everywhere. We see an x. So it's going to be 5 plus 3 divided by infinity to the power of 4. And so this is just going to be 5 plus 3 over infinity, because infinity times infinity times infinity times 4 times is just infinity. Now, 3 over infinity, this is a small number divided by a really, really big number. The answer there is going to be 0, but there's a 5 being added to the whole thing. So this is just 5 plus 0, which is equal to 5 eventually. So again, I'm seeing that the answer is not infinity or negative infinity. So that means, yes, I do have a horizontal asymptote. And we will say that y equals to 5 is a horizontal asymptote for the function 5 plus 3 divided by x to the power of 4. Now that we know the procedures for finding horizontal and vertical asymptotes, let's take a look at how this is actually done in a real example. In example number 3, we're given a function f of x, which is x squared minus 4x plus 4 divided by 3x squared minus 6x. And we're being asked to determine the location of any vertical and also horizontal asymptotes. Let me begin with horizontal asymptotes. So to find the horizontal asymptote of the function, we proceed by finding the limit as x goes to infinity or negative infinity of the function f of x. So it's up to you. You can decide whether you want to deal with infinity or negative infinity. In this case, I prefer to deal with infinity because it's just avoiding negative values, so maybe less mistakes will happen. And so let's look at the limit as x goes to infinity with x squared minus 4x plus 4 in the numerator divided by 3x squared minus 6x in the denominator. And because, again, because the x is going to infinity, the only thing that really matters is the leading coefficients and the leading term in the numerator and the denominator. So I get to ignore the negative 4x plus 4, and I get to ignore the negative 6x. And I'm just going to look at the limit as x goes to infinity with x squared divided by 3x squared. And obviously, I can reduce the x squareds to lowest terms, and when I reduce them, they get replaced with 1. So this is the limit as x goes to infinity with just simply 1 divided by 3. Since there are no x's to plug anything into, the limit is just simply going to be 1/3. So what does that mean? That means that the function f of x has a horizontal asymptote and its equation is y equals to 1/3. So the answer is yes, the function does have a horizontal asymptote and it's equal to 1/3. Now remember, if I had done the negative infinity version of this thing, I would reach the same result because again, I'm going to be plugging in negative infinity into the limit of 1/3, and that's going to be 1/3 as well. So this is why sometimes instead of seeing infinity down under the limit, you'll see people writing plus minus infinity like this. So this way you're doing both problems at the same time. So instead of writing infinity there, you would write plus minus infinity here. And again, because the limit has x going to infinity or negative infinity, you grab the leading terms from the numerator and the denominator. And again, regardless of whether you plug in plus or minus infinity, the limit will be the same because at this point in time, you're going to plug in nothing into the 1/3. There are no x's to plug in infinity or negative infinity into, and the result will be 1/3 either way. So this is why it's your preference, whatever you prefer, what you can deal with infinity or negative infinity, or you could do both like I just did here in this particular example. Now, let's look for the VA. So how do you find the vertical asymptotes? Now, to find the vertical asymptotes, again, you need to know the numbers that make the denominator equal to 0. So my denominator in this problem is 3x squared minus 6x, and I need to know what makes it equal to 0. Well, before I figure out what makes it equal to 0, let's try to factor it. And I see that I have a 3 and a 6. And I also have x repeating in both terms. So I'm going to factor the GCF. The greatest common factor is 3x. If I remove it from the first term, I'll be left with x and then a negative 2. And I need it all to be equal to 0. So what does that mean? That means either the 3x has to be 0 or the x minus 2 has to be equal to 0. This is because it's a product, and the zero product property says either the first term has to be 0 or the second term has to be 0 for the result to be completely equal to 0 at the end. Now, for 3x to be 0, it's enough for x to be 0, and for x minus 2 to be 0, we need x to be equal to 2. So there are two candidates, there are two options for VAs, but are they in fact both vertical asymptotes or not? Well, how do I find out? I can either find the limit as x approaches 0 from the left or the right and see if it's infinity or negative infinity and decide, or I could do the limit as x approaches 2 from the left and right and see if it's infinity or negative infinity and then decide. Or we can use a shortcut where we just take 0 and plug it into the numerator and see the form that we get. So if I put 0 into the numerator, the function becomes what? So the function returns 0 squared is 0, minus 4 times 0 is 0, plus 4 eventually. And on the denominator, I know the whole thing is going to be 0, because 3 times 0 squared minus 6 times 0 will be all 0. So this is of the form 4 over 0. So it's not 0 over 0. So this means, in fact, that x equal to 0 is a vertical asymptote of the function f of x. Now, let's try to do the same thing with 2. If I plug 2 into the numerator and denominator, what will happen is I'll end up with 2 squared, which is 4, minus 4 times 2, which is 8, plus 4, all divided by 0 again. And 4 minus 8 plus 4 will be 0 over 0. So this has the form of 0 over 0. So what does that mean? That means that this x equal to 2 is just a hole in the graph. It's not a vertical asymptote. So the function in this problem has one horizontal asymptote. So as x goes to infinity or negative infinity, the function is going to tend to stabilize, and it's going to stabilize around 1/3. And also there's a line, a vertical line, in fact, that the function cannot cross, and it's this x equal to 0, meaning the y-axis. So if I graph the function, I expect the function to go towards infinity or negative infinity before and after 0. So that's what I expect from the VA. And because of the horizontal asymptote, I expect the function to stabilize around the line equal to 1/3. So I expect it to be either here or there or maybe here or here towards infinity or negative infinity. And in fact, this is true. When you graph the function into your TI calculator, you'll see that as it approaches 0, meaning x equal to 0, the function goes up and down, as you can see it on the graph in front of you. And as the function goes more to the left or more to the right, the graph seems to stabilize. As a matter of fact, let me also put the 1 divided by 3, which is the equation of the horizontal asymptote. And you'll see that the graph of the function and the graph of 1/3 will tend to kind of overlap. Because my pixels are too big, the calculator will not be able to graph them separately. And you can see at the end, towards the left and right side of the screen, the blue line and the red line are sort of overlapping. So in real-world context, the horizontal asymptote refers to the value that the function is approaching as the input increases without bound. So let's look at example number 4, where we have a small pond that contains 12 units of dissolved oxygen in a fixed volume of water. At time equal to 0, a quantity of organic waste is dumped into the pond with the oxygen concentration t weeks later given by this formula that we're given. C of t equal to 12t squared minus 15t plus 12, all divided by t squared plus 1. So they want me to find the oxygen concentration 1 week after the waste was dumped, then 5 weeks after the waste was dumped. So the concentration level of oxygen is given by this function, and they want me to basically figure out what's happening if I plug 1 into this formula, and then what happens when I plug in 5 into the formula. So C of 1, it's a pretty straightforward procedure. You're just going to replace all the t's that you see with 1. So 12 times 1 minus 15 times 1 plus 12, all divided by the denominator, which is 1 squared plus 1. And you can plug this into your calculator, but you don't have to. This one is straightforward. 12 times 1 squared is just going to be 12 minus 15 plus 12 again, all divided by 1 squared is 1. 1 plus 1 is going to be 2 on the denominator. And basically, this is 24 minus 15, all divided by 2. So 9 over 2, which is 4.5. And so that's the end of part 1. And that's the end of what the concentration is 1 week later. So again, just plug 1 into all the places where you see T. Similarly, for 5, I'm just going to plug in 5 everywhere I see T. So it's going to be 12 times 5 squared minus 15 times 5 plus 12, all divided by 5 squared plus 1. So in this instant, I'm plugging in 5 into all the places where I see t into the function. And this one might require a calculator. When you plug everything into the calculator, it should be 273 divided by 26, which is roughly speaking 9.115. So those are the concentration of oxygen 1 and 5 weeks after the waste was dumped into the small pond. So as we can see from the paragraph and the numbers that we started with, on day 1, the pond had 12 units of dissolved oxygen. And as soon as you dump the waste into the water, it seems like the oxygen level really dropped to 4.5. But as time went on, 5 weeks later, it seems like the oxygen level is back up to about 9 units of dissolved oxygen. So it seems like the pond is recovering, and that's what we're going to try to find out in part number 2. It says find the limit of the concentration as time passes on towards infinity. So as you let time go on, so as you let more weeks pass by, what's the concentration of the oxygen in this pond? So to do this, I'm just going to take the limit as t goes to infinity and figure out what it's going to be. So the limit as t goes to infinity, the function is 12t squared minus 15t plus 12, all divided by t squared plus 1. And so again, my limit has the variable, in this case t, approaching infinity. So the only things that really matter to me are the leading terms in the numerator and the denominator. So in this case, the 12t squared and the t squared from the denominator. So we can pretty much ignore everything else. That's because the time is going towards infinity. So more and more weeks are passing, and we're trying to figure out what's happening with the concentration levels of oxygen in this pond. So 12t squared divided by t squared. Obviously, I can reduce it to lowest terms. I can divide out some t squares from the numerator and denominator. And when I divide them out, it's just going to be a limit with t going to infinity and just simply 12. There are no more t's left over in this expression. So it's just the limit of 12, and the limit of 12, regardless of where t is approaching, it's going to be equal to 12 also. So that means that the concentration levels of oxygen are approaching 12 as time passes. So it seems like the pond is recovering. We started off with 12 units of dissolved oxygen on day one. Then somebody dumped the toxic waste and the levels of oxygen dropped drastically. But if we let time pass, it seems that the pond is recovering and the oxygen level is going back to 12. Let's take a look at the graph of this function and see the graph. So to graph it, we do the same procedure as usual. So I'm going to use x instead of t on my calculator. So everywhere I see a t, I'm just going to write the letter x instead, just because I don't have a t here. But this is the numerator, and my denominator contains multiple variables, so make sure you use some parentheses again. And so this is the expression or the function that we're given. I'm going to click on zoom and just pick the standard zoom, which is zoom option number 6. And I'm seeing part of the graph, I'm not seeing the full picture, so let's modify this image a little bit so we can see more of the graph. I don't care about negative time, so this whole section on the left side is removable. I'm just going to start my time at 0, and so you can see it's already improved. It seems like the oxygen level is never negative, so I don't see the point of having any negative y coordinates, so I'm going to go ahead and remove the y minimum. Instead of negative 10, I'm going to make it 0. And there's the graph so far. Let's do one more improvement. I'd like to see more of the top of the graph and maybe more of the right side of the graph. So I'm going to go back to window, and I'm just going to change my x maximum. Instead of 10, I'm going to make it 20. So this is basically 20 weeks, let's say. And the y maximum, let's make it 15. So you can see this is what the graph looks like. And just a couple of things to point out. If I click trace and trace 0, you'll see we started off with 12. So 12 units of oxygen were dissolved in this pond at the beginning of the experiment. We can see that on the graph. After 1 week, so what happens after 1 week? We plug in 1, and you can see that the level dropped to the lowest possible value, 4.5. So that's when somebody dropped the toxic waste. The oxygen levels in this pond just shot down drastically. But after 5 weeks, it seems like they are on the way up. And as we let more weeks pass by, you can see that the y coordinate that we're seeing is starting to look towards 12. So as more and more weeks pass by, you'll see that the y coordinate is going to approach 12. So there we go. This is at 19 weeks and a half. We're already at 11.2. But let's let time pass by even more. So I'm going to increase the number of weeks that pass by from 20 to 40 and click on graph again. And you can see, I'll just put it straight at the end. Let's go to week 39, for instance. You can see the level of oxygen is not quite 12 again. It's at 11.6. But obviously, as more and more weeks pass by, our theory, the calculation says that we should eventually go back to 12. Let us finally discuss curve sketching of rational functions. So when we curve sketch, our goal is to use our knowledge of algebra and calculus to create an accurate and complete graph of the function. And the complete function of a graph shows typically the intercepts, the discontinuities, any holes or vertical asymptotes, any horizontal asymptotes, maximas and minimas, the concavity, and inflection points. Typically, before you begin sketching a problem, you should always find the domain of the function because it will help you out with a few of these goals. For instance, the vertical asymptotes, and it may tell you something about maximas and minimas. So it's usually a good idea to find the domain of the function first, then determine the intercepts. The easier option is to find the y-intercepts first, because you just need to plug in 0 into the function. But sometimes finding the x-intercepts is difficult, so if that's the case, then just don't bother finding them. And next, usually what you do is you analyze the first derivative and you determine the places where the function is increasing or decreasing, and that will also tell you the maximas and minimas of the function. And finally, you'll typically analyze the second derivative to give you information about the concavity and the location of the inflection points. Once you've done all these steps, you typically want to put it together using graph paper or just simply the graph that's provided to you. It's always a good idea to check your answer at the end by plugging the function you're working with into your calculator and seeing if you get similar graphs. So we will illustrate all these steps with example number 5, where the function is f of x equal to 3x over x plus 2. In part 1 of the problem, it says to find the domain, any vertical or horizontal asymptotes, and the intercepts. So let's start by finding the domain of the function first. So to find the domain of the function, in this function, I'm seeing a denominator, which is x plus 2. So obviously, it's bad if the denominator becomes 0. So when will the denominator x plus 2 become equal to 0? This happens if x is equal to negative 2. So negative 2 is basically a forbidden number, so my domain is going to contain everything except that value. And so how do I say that? Using the set builder notation, I say x could be anything as long as x is not negative 2. So that's one way to do it. Or you can say it in interval notation by saying the domain is every number from negative infinity to negative 2, but not including negative 2. That's why I'm putting parentheses there. And then also every number from negative 2 all the way to infinity. And again, it doesn't include negative 2. That's why we're putting parentheses. So that is the answer to domain, and we're done with that. So next, we are going to look for any asymptotes. So are there any asymptotes? How do we find asymptotes? So there are two types of asymptotes, the vertical and the horizontal asymptotes. Let's start with horizontal asymptotes first. The procedure is to just take the limit as x goes to either plus or minus infinity. So it's up to you. You could either do plus or minus, but I'm going to do both at the same time here in this problem. So this is basically the limit as x goes to either plus or minus infinity, and the function is just simply 3x divided by x plus 2. Now, because I'm going to infinity or negative infinity, it does not matter regardless. The only things that matter on the numerator and the denominator are the leading terms. So in this case, 3x and x. So I get to ignore the 2 for the moment because I'm doing a limit and my limit is approaching infinity. So this is just the limit as x goes to either plus or minus infinity with 3x on the numerator divided by x on the denominator. And we can simply divide out the x's, and we will end up with a limit as x goes to either plus or minus infinity, regardless, with 3 times 1 divided by 3. 3 times 1 divided by 1 is just going to be 3 at the end. And regardless of where my limit is going, whether it's going to plus or minus infinity, the limit of 3 is just simply 3. So it seems that we will have a horizontal asymptote. So yes, there is a horizontal asymptote. The y equal to 3 is the horizontal asymptote. So as the graph stretches to the right and left side of the page, the graph should stabilize at 3. It should not go up forever, it should not go down forever. It should just stabilize where y equals 3. Now, the other type of asymptote is the vertical asymptote. And to find the vertical asymptotes, we'll just look at the domain. The domain used to have all the numbers except for negative 2. So negative 2 is the bad value. That is the candidate for a VA. And to quickly decide, I'm just going to plug the negative 2 into the function and see the form that I get. Do I get 0 over 0? Or do I get some random number divided by 0? Now remember, the function is 3x, so I'm going to have 3 times negative 2 divided by x plus 2. So the x I'm plugging in is negative 2, but there's already a plus 2 on the denominator. Remember, this is the function 3x over x plus 2. So if I plug the negative 2 in, I'm going to see a negative 6 on the numerator and a 0 on the denominator. This does not have the form 0 over 0. So what does this mean? This means, yes, in fact, x equal to negative 2 is a vertical asymptote on this graph. So the function has kind of a border at x equal to negative 2 that the function cannot cross. So it's going to tend to go either to plus or minus infinity before and after this value. So far we've answered domain, we've answered vertical and horizontal asymptotes. The only thing that's left is intercepts. So how do I find intercepts? Again, for intercepts, there are two types of intercepts, either x-intercepts or y-intercepts. Let's start with the y-intercept first. So to find the y-intercept, we will just let x be equal to 0. So in other terms, we're going to plug 0 into the function, and that's going to be 3 times 0 divided by 0 plus 2, because it used to be 3x over x plus 2. 3 times 0 is 0, divided by 2 is just simply 0. So what does this mean? This means that the point that belongs to the function is 0, 0. So 0, 0 is a point on the function. It's actually the y-intercept. Now, it's silly for me to look for the x-intercept because I know it's going to be the same number because 0, 0 is both on the x-axis and the y-axis, but let's do it for the sake of completeness. If I'm looking for the x-intercept, I'm going to let the y be equal to 0. So in other terms, I'm going to let f of x become itself 0. So I'm going to have 0 equal to 3x divided by x plus 2. And regardless of how you solve this equation, you can cross multiply things and imagine that 0 has an invisible 1 underneath it. In other terms, you're saying 3x needs to be 0. So regardless, again, x itself is going to be 0. We kind of already knew that when x is 0, the y will be 0. So if y is 0, then x has to be 0 as well. So again, we're getting that the point that belongs to the function is 0, 0. So again, 0, 0 is both the x-intercept and the y-intercept. This does not happen very frequently, but it did happen for this problem. So far, from all this, we can see that y equal to 3 is an important location, x equal to negative 2 is an important location, and 0, 0 is an important location. And like I said, we did it twice, but we didn't have to do it the second time. We also know that the domain does not contain the value negative 2, so that's another important location to pay attention to. Okay, so now it's asking us to find the maxima and minima and also the points of inflection. So remember, what does this mean? This means that we need the first derivative and the second derivative. So keep in mind that the function f of x is 3x over x plus 2. So first things first, let's look for the derivative f prime of x. So this is going to be a quotient rule. So low d high minus high d low, square the bottom, and off you go. So the derivative will be 3 times x plus 2 minus the derivative of the denominator is just 1 times the numerator, which is 3x, all divided by the old denominator squared, and then off I go. So in other terms, this is just 3x plus 6 minus 3x, all divided by x plus 2 with the whole thing squared. The total here is just 6 divided by x plus 2, and every one is squared. So that's my first derivative. And what numbers make it equal to 0? What numbers make it undefined? So for f prime to be equal to 0, I need to look at the numerator. The numerator is 6. 6 cannot be 0 because it doesn't have any x's near it. So there is no solution for that part of the problem. Now, what about the denominator? What makes the function f prime of x undefined? So to figure out what makes the function undefined, you'll take the denominator and you'll set it equal to 0. But that implies again that x has to be negative 2. So negative 2 is the only critical value. Now keep in mind that x equal to negative 2 is also not inside the domain, so don't mislabel it as a maximum or minimum. It's actually just a random point that does not belong in the domain of the function f of x. So it's a critical number nonetheless. So now I'm going to do my first derivative test. So the only value that we found from all this work so far is just -2. So I'm going to put -2 there. And instead of putting a little notch like I always do, I'm going to put a little circle to remind myself that I cannot call it a maximum or a minimum. Remember, it was not part of the domain, so it cannot be called a maximum or minimum. So that's why I'm putting the little circle here around -2. So that way I remember to not mislabel it. Now I need a number before to test, and I need a number after to test. So I'm going to test x equal to -10 from the left side, and I'm going to test x equal to 0 from the right side. Now when I'm testing, I'm going to plug 0 into the derivative to see if it gives me a positive or a negative answer. I'm going to plug -2 into the derivative to see if it gives me a positive or negative answer. So starting with 0, because it's the easier one, we'll have 6 divided by 0 plus 2, everybody squared, and the result will be completely positive, because 6 divided by 4 is a positive value. So what does that mean? That means that the function f of x will be increasing on this interval from -2 all the way to infinity. Remember, this is the first derivative, and that's why we're saying that the function is increasing. Now, what about -10? If I plug -10 into this derivative, I'm going to end up with 6 divided by -10 plus 2, everybody squared. So this is basically 6 divided by -8 squared. And again, regardless of what you do, what the number is, in fact, it's going to be just simply positive. Because -8 squared will become a positive value, 6 divided by a positive value will still be positive. So again, the function f of x will also be increasing on the interval before -2. So we don't have any maximum, we don't have any minimum, we just have a function that increases before and after the value -2. So next, what I'll need to do is figure out the inflection points, and to do that, I need the second derivative. Now keep in mind that the first derivative was just simply 6 divided by x plus 2 with the whole quantity squared. I'm going to rewrite it as 6 times x plus 2 to the power of -2, so that way when I find the second derivative, I can just use the chain rule instead of the quotient rule. It's a little bit faster. So with that in mind, what would the second derivative be? So 6 is going to hang out, -2 is going to come down from the power, x plus 2 is going to stay there in the base, the power is going to lose 1 because of the chain rule, and then I need the derivative of x plus 2 afterwards. Well, it's just a 1, so whether you write it or not, it's not going to matter, so I'm just going to erase it. So what's my second derivative equal to? It's going to be -12 with x plus 2 to the power of -3, and I can just write it as -12 over x plus 2, the whole quantity cubed. So again, I need to know what makes it equal to 0, what makes it undefined, so let's try again. What would make the f double prime equal to 0? Well, in this problem, my second derivative does not have any x's in the numerator, so again, there is no solution to this part of the problem. There is no solution because there is no number that makes -12 become 0 suddenly magically. There has no x. There needs to be x there, and there's no x next to the -12. Now, what about the second option? What about what makes the f double prime undefined? So for the second derivative to be undefined, I need the denominator, x plus 2 cubed, to be equal to 0. And the number that makes it equal to 0 is just, again, -2, as usual. But again, keep in mind that -2 is technically not allowed in the domain, so don't mislabel it. Don't say that it's a inflection point. It's just a place where the concavity may or may not change. So to find out, let's do the test. So here's the number line from -infinity all the way to +infinity. -2 is somewhere in the middle, and again, I'm gonna put a little circle instead of a little tick. because I want to remember that I cannot call it an inflection point. So again, I need some test values before and after. So pick your own, but I'm going to choose, again, 0 from the right side and -10 from the left side. Now, putting 0 into the second derivative, you will see that you'll end up with -12 divided by 0 plus 2 everybody cubed. And that's going to be a negative amount when you divide it all out. So what does that mean? That means that the function f of x is concave down on this interval because my second derivative was negative. Now what about -10? If I plug -10 into the second derivative, I'm going to see -12 on the numerator and -10 plus 2 all cubed on the denominator. This is just simply -12 divided by -8 cubed. -8 cubed is going to be a negative value, and -12 divided by negative is going to be a positive amount. So this is going to be a positive amount. And so therefore, the function f of x will be concave up on the interval before -2. And I'm just going to erase everything else because it's not relevant. So now that we have all this information, let's try to summarize it on this graph, and then we will check our calculator to see that we got the correct sort of picture. So first things first, we know that 0, 0 is the place where the function crosses both the x-axis and the y-axis. We also know that we have some vertical asymptote and some horizontal asymptote. As a matter of fact, we know that we have a horizontal asymptote when y is equal to 3. So let me make a dotted line where y is equal to 3. So this is that location. So my function will be close to it at the end, either here or there, and close to it at the end here or here. So those are the places where the function may be found at the end. We also know that there's a vertical asymptote at x equal to -2. So I'm going to make that in blue this time. So at -2, we have a vertical asymptote. So we know that the graph of the function will be either here, or at the bottom here or there. So those are the only places where the function can be, because these are asymptotes. They basically trace the function. So what else do we know? We know that there's some places where the function was increasing and decreasing. So where was the function increasing and decreasing? If we go back to our notes, we know that the function was always increasing no matter what. So no matter what, the function is always increasing before or after -2. So we know that the function has to be going up on the interval. So maybe it's going up from here to there. That would make sense because it cannot be going up this way, because then it would have a crossing on the x-axis, and that's not permittable, that's not allowed. We don't have an x-intercept. So I'm thinking that we can already remove these two locations. We think that the graph is going to go up from here to there. This is kind of what the graph should be doing on this side of the xy plane. Now, how is it doing it? It's doing it in a concave up manner. So I know that the graph should be concave up, sort of, on this section. And on the other side, I also know that the function is increasing from -2 all the way to infinity. The function is increasing, but it's doing it in a concave down manner. So I'm thinking, since I have to cross through that point, it seems like the logical thing would be for it to be doing this sort of thing. So this is what I'm expecting, and this is what I'm expecting on this side. So now, if I want more accuracy, I can find some additional points. So I can plug x equal to 1 into the function. I can plug x equal to 2 into the function, and so on and so forth, to get more accurate graph, right? For example, over here, is the graph doing this? Is it hugging the lines very much so? Or is it doing this kind of thing? Is it just going from those parts to the other part, but far away from the asymptotes? So we don't have any information. We did not look for it. So we Know, though, that the graph is going to be doing this sort of thing. So that's what the important part is, that we are going to be approaching the asymptotes on the left and in the middle. We also know that the graph should be crossing through 0, 0, and it has to be increasing, so it's going to look like this, while also maintaining a concave down look to itself. Now, to verify whether our graph is accurate or not, we can plug the function into the calculator and get an accurate representation of what the graph should look like. But generally speaking, this is the graph that we are expecting. It matches with all of our work. So let's confirm with our TI calculator. So plugging in 3x divided by x plus 2. And I'm going to click zoom 6 to make everything standard. We can see that the graph looks exactly like our prediction. I'm going to add an extra line over here, which is the line y equal to 3, so we can see that it is in fact a horizontal asymptote. So that's the horizontal asymptote, and I can't graph the vertical line x equal to -2, but you can sort of imagine that it's there. So I'm going to trace values around -2 for you to see. So first of all, -2 gives me no y coordinate. That's because -2 is not part of the domain, so there is no solution. The function is undefined at -2. But before and after -2, you can see that there are values. And if I am slightly before -2, you can see that the y value is like 52. Then it goes to -195. So it's doing this little jump from here. The calculus is doing the jump from here to there very, very quickly, and I'm not able to see it very accurately. But anyway, if you want to make the graph on your paper a lot more accurate, you can trace additional values. So for example, you can trace -3. As you can see, -3 gives me y equal to 9. So I know that when x is -3, I should be around 9, which is sort of where I was. So, if you want to make it more accurate, you can trace additional points. There's another option, -4 gives me 6. So -3 gave me 9, -4 gives me 6. So you can get additional points to connect the graph and make it as accurate as possible. But remember, this is just a sketch. So as long as it looks sort of like what we are looking for, then you'll be fine. And so this is the general shape that I'm expecting. I'm expecting to start here and there, and also start here again and end here at the end. So that's how you graph rational functions. And we will do it again on the next page with a different function this time. So this time the function f of x is 2 divided by x squared plus 1. And again, we are asking for the domain, vertical, horizontal asymptotes, and any intercepts. So for the domain of the function, in this case, the domain is going to be all real numbers because there's no value that makes the denominator equal to 0. It's literally impossible to make x squared plus 1 equal to 0. So the domain is from -infinity all the way to +infinity. So that means there will not be any vertical asymptotes. So i.e., there is no vertical asymptote. There is no number that makes the denominator 0 to plug in the numerator. So there is no vertical asymptotes. Now, what about horizontal asymptotes? So for HA's horizontal asymptotes, we'll take the limit as x goes to either plus or minus infinity on this function f of x. And so the limit as x goes to either plus or minus infinity of 2 divided by x squared plus 1. We can sort of ignore the plus 1 because we're approaching infinity or -infinity. So the only things that matter on the numerator are 2 and on the denominator x squared. So we could just ignore the 1. And so regardless whether you put plus or minus infinity into the x, it's going to be 2 divided by infinity, which is 0. So this, in fact, says that the y equal to 0 is a horizontal asymptote. So I'm expecting the graph to be really close to the x-axis on the left side and on the right side of the page. So far this is important, and also the domain is definitely important. So we've answered multiple questions so far. We've answered the domain, vertical and horizontal asymptote. The only thing that remains is the intercepts. So there are two types of intercepts. So let's begin by finding the y-intercept. So, y-intercept. So to find the y-intercept, we're going to let x be equal to 0. So this means that I'm going to put 0 into the function f of x. And this will be 2 divided by 0 squared plus 1, which is 2 over 1, which is just simply 2. And so the point on the function is called 0, 2. Now, there is a second type of intercept called x-intercept. And for the x-intercept, I need to let the y be equal to 0. So in other terms, I need to figure out the answer to this equation, 0 equals to 2 divided by x squared plus 1. And so again, there's different ways of doing it. You can imagine there's a 1 here and just cross multiply. But when you do that, you will end up saying that 0 is equal to 2, because 0 times x squared plus 1 is 0, and 2 times 1 is equal to 2. And 0 equals to 2 is nonsense. This is not possible, so I'm going to say that there is no solution to that part of the problem. So we only have one intercept, which is 0, 2. We only have one type of asymptote. It's a horizontal asymptote, y equal to 0. And that's it. We're done with part 1. So next for part 2, it's asking us to find the maxima, minima, and points of inflection. So again, we need the first and second derivative for this. So let's recall the function f of x. It's on top of the page. The function is 2 divided by x squared plus 1. So I can rewrite it like 2 times x squared plus 1 to the power of negative 1. So this way I can avoid doing the quotient rule when I find the first derivative. So anyway, let's find the first derivative. And so because I'm avoiding the quotient rule, I'm going to have to use the chain rule. So 2 is hanging out. The negative 1 is going to come down from the power. X squared plus 1, it used to have negative 1. It's going to subtract another negative 1 because of the derivative. And then I need the derivative of the inside afterwards. The derivative of x squared plus 1 is just simply 2x. Let's clean everything up. So we have a bunch of products in the middle of these parentheses. So 2 times negative 1 is going to be negative 2. Times 2x is going to be negative 4x. And this is x squared plus 1 to the power of negative 2. I'll write it as x squared plus 1 squared. Or if you prefer to keep it negative exponent, it's fine. You can keep it that way. I'll rewrite it like this for now. So this is my first derivative, and so what makes it equal to 0? So my first derivative is a fraction. For a fraction to be equal to 0, I need the numerator of the fraction to be itself equal to 0. So I need 4x with the negative to be equal to 0. So that means I need x itself to be 0. Because if I divide by negative 4 on both sides, 0 divided by negative 4 will still be 0. So x is equal to 0. So this is the first part. And now I need to know what makes the derivative undefined. So again, my derivative is a fraction, so for it to be undefined, the denominator, x squared plus 1 squared, has to be 0. And again, there's no solution to this part of the problem because there's no chance on earth that the inside here, x squared plus 1, can be 0. There's no x value that makes it 0. So we have only one critical number, and that's the only one we have to worry about, which is 0. So let's draw the number line next and do some testing. So here we go. This is the number line representing all the numbers from negative infinity all the way to plus infinity. The only critical number that we found is 0. There was another critical value that we kind of paid attention to earlier. So we know that this is also going to be the y-intercept. But anyway, let's do some testing. So we'll test some numbers before and after. I'll test negative 1 and positive 1 this time, just to add some variety. And I'm going to plug them into the derivative to see if the derivative becomes positive or negative. Remember, this is the first derivative test. I'll let you do the testing, but I believe when I plug in 1 into the derivative, the answer is going to be a negative amount. And when I plug in -1 into this derivative, the answer is going to be a positive amount. And you can confirm that by using your calculator, or you can just do it by hand. It's up to you. Regardless, this is saying that the function f of x is increasing before 0, and the function f of x is decreasing after 0. And remember, 0 has a second coordinate we found. It's 2. It's the y-intercept. So it seems like we're climbing to that y-intercept, then we're going downhill after the y-intercept. So that's the first derivative, and that's going to tell us that x equal to 0 is a maximum. X equal to 0 has a maximum. We still need to know whether there's inflection points or not. So for that, we need to know the second derivative. So keep in mind that the first derivative is -4x all divided by x squared plus 1 with the whole thing squared. So that's my first derivative, but now I need to know the second derivative, and it's going to be a little bit tedious, but we can do it together. To find the second derivative, I need to use a quotient rule. But this time the quotient rule is going to be ugly because it would also include a chain rule. So to make life easy, I'll label the numerator and I'll label the denominator as 1 and 2. The numerator is -4x. The denominator is x squared plus 1, everyone squared. Let's find the derivatives of these guys separately before we start the quotient rule. Derivative of -4x will be -4, but derivative of x squared plus 1 will be 2 times x squared plus 1 to the power of 1, because we subtract 1 from the power, times the derivative of the inside, which is just simply 2x. So ultimately, this is just going to be 4x times x squared plus 1. And my quotient rule tells me to multiply 1 prime 2, 2 prime 1, subtract, square the bottom, and off you go. So now that we have all the parts ready, let's put it together. -4 gets multiplied with x squared plus 1 squared. The rule tells me to put a minus sign next. Then I have to multiply this corner with this other corner. So it's going to be 4x with x squared plus 1 multiplied by the other corner, -4x. It's all divided by the old denominator, x squared plus 1 squared, but we have to square it again because of the quotient rule. So it's a little bit tedious, but that's how rational expressions usually work. So don't worry about it. Just practice doing derivatives and you'll be fine. So anyway, now it's time to clean up this derivative and figure out what makes it 0 and what makes it undefined. So you know what? Let's do this first. I'll keep everything as is for now. I'll just multiply this part over here. -4x times -4x will be positive 16x squared. And I'm going to leave everything else alone. The denominator already has x squared plus 1, but now it has double squares, so that's technically raised to the power of 4. Now I'm going to imagine that I have one box here, another box here, and a third box below on the denominator. And all those boxes contain x squared plus 1. As a matter of fact, this first one actually has x squared plus 1 squared. So I'm going to remove x squared plus 1 from each of the boxes. I'm going to just divide out x squared plus 1 from each of the boxes. And when I do that, things should clean up a lot better. So from the first box, removing x squared plus 1, we will be left with -4 and an extra x squared plus 1. The second box is going to lose the x squared plus 1. It's just going to be 16x squared remaining. And the final box on the denominator loses one of the x squared plus 1s, so that means 3 will remain. So that's the derivative, a little bit cleaner. And now finally I'll just multiply and combine like terms in the numerator. So on the numerator I'm going to have -4x squared minus 4 plus 16x squared. That's the same thing as saying 12x squared minus 4 instead. And on the denominator, I can just leave x squared plus 1 with the power 3. So since this is going to take a lot of space, I'm going to shrink this down a little bit so we can fit the rest of the problem on the same page. Here we go. So that's my second derivative already done. So now I need to know what makes it equal to 0 and what makes it undefined. So the numbers that make it equal to 0 are the numbers that make the numerator 12x squared minus 4 equal to 0. And by the way, this is the same thing as 12x squared equal to 4. We can divide 4 on both sides. So this is saying that 3x squared has to equal 1, which means that x squared has to equal 1/3, which means x is either plus or minus the square root of 1/3. Now, what makes the second derivative, undefined? The answer is, again, nothing. So we need x squared plus 1 to the power of 3 to be equal to 0, and this will not have a solution because there's nothing that makes x squared plus 1 itself equal to 0, so the cube of it will not be 0 either. So we ended up with two critical values in this case. So let's go ahead and draw the number line now and figure out whether the function is concave up or down and whether we have inflection points or not. So the only critical numbers are the square root of 1/3 and the negative version of that. And so we need some test values. I'm going to test some random numbers. The numbers I'll test are, let me use red. Are -10 and 0 and 10. Now when I do the testing, I'm actually going to ignore the denominator. The testing has to happen in this derivative, 12x squared minus 4 divided by x squared plus 1 to the power of 3. I'm going to ignore the denominator because x squared plus 1 will always be positive no matter whether I plug in -10 or 0 or 10 into it. It's going to be positive anyway, and so if I cube it, it's going to be positive still. So to save myself a little bit of time, I'm just going to plug the numbers that I'm testing just in the numerator. And this is a cool trick to use if you don't have a calculator and you just want to get things done quickly. Let's start with 0. If I plug 0 there, I'm going to end up with 12 times 0 squared minus 4. And so that's going to be 0 minus 4, which is a negative amount. Because it's a negative amount, that means the function f of x will be concave down on this interval. Now, if I plug 10 into the numerator, I'm going to have 12 times 10 squared minus 4. So 10 squared is going to be like 100. 12 times 100 is going to be a massive positive number. Minus 4, the minus 4 is not going to matter. The result will still be positive here, which means that the function f of x will be concave up on that second interval, or rather third interval. And finally, -10. If I put -10 into this x, I'm going to have basically 12 times -10 squared. -10 squared will be positive 100. Multiplied by 12 is going to be ridiculously large. Take away 4, it's not going to matter. It's still going to be positive. So the function will also be concave up on this interval as well. So we went from concave up to concave down to concave up again. So what does that mean? That means that x equal to negative square root of 1/3 is an inflection point. And also x equal to 1/3 square root is an inflection point as well. So we do have, in fact, two inflection points, the square root of 1/3 and negative square root of 1/3. Now, we need to put it all together in this graph that I've provided. So a few things right off the bat. We have a horizontal asymptote. So let's go ahead and add it in red. The horizontal asymptote we found was the y equal to 0. So the x-axis basically. So make sure that you don't cross this line. We have an intercept at 0, 2. So we know at this location, we are going to be crossing the y-axis. And also, in fact, we discovered that there's a maximum when x is equal to 0. So this point itself is a maximum location. So the highest point on the graph is there. We also have some inflection points, the square root of 1 over 3 and the minus the square root of 1 over 3. So those are some decimals. They're slightly smaller than 1, and 1 is basically here. So somewhere before 1, there's an inflection point. Somewhere between -1 and 0, there's another inflection point. I don't know if it's going to be high here or maybe there, but I know that somewhere before and after 0, there's a couple of inflection points. So in other terms, this is where the concavity is going to change. So what else do we know about the function? We also know that the function is increasing until it reaches the maximum, then decreasing afterwards. So okay, let's try to put it together. I have to be close to the asymptote. So I have to be either above or below the asymptote. Can I be below it? The answer is not possible. Because if I'm below it and I need to get from here to there, I would have to cross the y-axis somewhere, and I'm not allowed to cross it below. I have to cross it up at 0, 2. So I can automatically remove the bottom options. Those are not valid. They're not consistent with everything else we know. We also know that the function has to be increasing until it gets to the maximum, then decreasing afterwards. Now, how does it do it? It does it first by being concave up until it reaches the inflection point, then it switches concavity. So regardless of where this point is, I didn't find the y-coordinate, it may be here or it may be there, I don't know, but I have to be concave up until I get to it, then I have to be concave down afterwards. And I also know that afterwards, my function is going to be decreasing forever. So from the maximum, it has to decrease. And how does it do it? It does it first by being concave down, then by being concave up. So in other terms, from the inflection point to the inflection point, I have to be concave down. That kind of makes sense. We're crossing from the inflection point to the other inflection point, going through the maximum in a concave up way. So that's kind of what I'm expecting there on that interval. And I have to get to the edges of the graph by being concave up. So something along this graph, something along this line. So that's the general picture that I'm expecting to see when I plug my function into the calculator. Now again, to get more accuracy, I can go ahead and plug in 1, 2, 3, and so on into the equation of the function to get some actual estimates for the y-coordinates, but I'm deciding to skip it here and use the calculator to do the work for me. So let's go ahead and try to find out what the graph looks like on the calculator. So I'll begin by plugging the equation in, 2 divided by x squared plus 1. And I'm going to click zoom number 6 to reset the window. And you see the graph barely visible there. So there's a lot of empty spaces that we don't need to see. So let's go ahead and make some adjustments to the window. So for the x minimum, x maximum, I like the values -10 and 10. They match with what we have on paper. And on paper, we have a y minimum at -1, and it seems like the y maximum, they've put it at 3. So let's look at the graph now, and there we have it. This is what the graph looks like, and let's now look at the inflection point. So where's the inflection point? I'm going to trace the square root of 1 divided by 3, and I'll show you the inflection point. There it is. So the y-coordinate is 1.5. And let me trace the other inflection point, which is the other side, negative square root of 1 over 3. And again, the y-coordinate is 1.5 because of the symmetry. So with that in mind, I can go back to here and make the graph a little bit more accurate. So my inflection points are happening at 1.5, so halfway between 1 and 2, there's an inflection point there and another one there. I know the graph is going to be concave down between those guys, so I'm going to make it look like this, like an upside down U shape. And on the other side, we're just going to connect the edge to the inflection point, and similarly on the opposite side. And this is what our final graph will look like. Obviously, you want to make it as smooth as possible, as pretty as possible, but it doesn't have to be perfect. It just has to look correct. And really, what matters is everything else you did before, finding the derivative, finding the inflection points, and so on and so forth. That's worth more points than the actual graph itself.